ME347, Example 21. For this problem, use the same system described in Example 19 and the same pump family, which is the Peerless 4AE12 pump family operating at 1750 revolutions per minute. For Part A, calculate the specific speed in customary units for the system operating at a flow rate of 400 gallons per minute and using a pump operating at a speed of 1750 revolutions per minute. For Part B, compare your answer to Part A for the system to the specific speed for the four largest pumps from the Peerless family, also operating at a speed of 1750 revolutions per minute at the best efficiency point. For this problem, we need to make the same assumptions made to calculate the system curve in Example 19. These include the following. First, we assume steady, constant property flow of an Newtonian fluid, which is water at 60 degrees Fahrenheit. Second, we assume that the water in the large tanks has a constant height, that is open to the atmosphere, and that the velocity to top is approximately 0. Third, we assume fully rough turbulent pipe flow near the operating conditions for the pump. Let's begin by looking at the schematic diagram from Example 19, which shows water being pumped upwards from a lower tank to an upper tank. The water in the lower tank first enters the piping through a re-entrant entrance with a loss coefficient of 0.78. Then it goes through 10 feet of piping and 1 elbow before the pump suction inlet. After the pump discharge, it goes through 40 more feet of piping and 1 additional elbow before flowing into the upper tank through an abrupt exit with a loss coefficient of 1.0. For both of the elbows, the minor loss is given in terms of an equivalent length of straight piping. Note that the pipe has a diameter of 3 inches, a roughness of 0.0050 feet, and a total length of 50 feet. Also, the change in elevation of the water before the pump is 5 feet, and the change in elevation after the pump is 20 feet. Thus, the total elevation change is 25 feet. Note that this data was used in Example 19 for Part A to find the system curve, and for Part B to find the operating conditions for the 11-inch diameter pump as shown. For Part A, calculate the specific speed in customary units for the system operating at a flow rate of 400 gallons per minute and using a pump operating at a speed of 1750 revolutions per minute. To begin, we recall the definition of the specific speed as shown, which is a parameter that compares the operating speed to the operating head. If a consistent set of units are used, the specific speed will be dimensionless. However, the units will not cancel if it is calculated using the customary units that are also shown. Recall that for a low specific speed, less than about 0.5 if dimensionless, and less than about 1500 for customary units, radial flow pumps will typically be more efficient. Conversely, for high specific speed, greater than about 4 if dimensionless, and greater than about 10,000 for customary units, an axial flow pump will typically be more efficient. To calculate the specific speed for our system, we first calculate the operating head at our desired flow rate of 400 gallons per minute and get a system head of 98 feet. Substituting in these values, we get 1,124 for the specific speed. Thus, a radial flow pump would typically be selected for this system. For Part B, compare your answer to Part A to the specific speed for the 4 largest pumps for the Peerless family, also operating at a speed of 1750 revolutions per minute at the best efficiency point. To begin, we need to refer to the pump performance curves for the Peerless pump family. Recall that the best efficiency point corresponds to the maximum efficiency, which is indicated on our plot by the red line at the center of the efficiency contour lines. We then use the intersection of this line with each of the pump curves to get the operating conditions at the best efficiency point. For example, the 9.5-inch pump will operate at a flow rate of 430 gallons per minute with a head of 75 feet. We then read off the operating points for the remaining 3 pumps at the best efficiency point and list the results in the table shown. From these conditions, we repeat the calculations from Part A to get the specific speeds listed in the last column in customary units. Note these are radial pumps, which is consistent with the calculated specific speed magnitudes that are all below 1500. Comparing these values, we find that the calculated system value is between the specific speeds for the 11-inch and the 12.12-inch diameter pumps. Thus, either pump will be operating near its best efficiency point when used with this system. In particular, the 11-inch pump will be just below, and the 12.12-inch pump will be just above.